So yeah, two equation models. So what have we done so far? We've looked at algebraic models, the most famous ones. We've looked at one equation models, and now we'll turn our attention to two equation models. And probably the two most popular two equation models are K epsilon and K omega. And K omega came first, and that's why it's probably good to look at K omega first. And the K epsilon came second in terms of development. And there's probably way more K epsilon models that are running in existence, but both are used equally. Probably in my own research, I've probably ran more K omega type models in a particular form of them, which we'll talk about near the end of this two equation module. And they both are like a dissipation type quantity, which is like a rate at which the turbulent kinetic energy is being dissipated into the flow. So let's make some introductory notes about two equation models. Obviously, they're today the foundation and workhorse of design and engineering and prediction, and they make really good prediction. And typically there's one variable, not always, but usually it's K, which is the turbulent kinetic energy. So that's going to be one partial differential equation. And the second one sometimes might be, you can choose anything for a second variable if you can create a PDE for it. It might be length scale or something else. Maybe it's a time scale. So these are very popular second equations. But you can see the most popular is epsilon or omega, and we'll see both of these forms in a little bit. And another great thing about these models in general is that they're complete, or most of them are complete, meaning what? That no other information has to be supplied about the solution before you run your code. So for example, in the Spalart's model or Prandtl's model, we're saying, oh, there's something about the length scale and its distance to the wall. So typically, like in Spalart's model or similar models, before the code runs, you got to find D. Well, that's totally absent. And a lot of these models are also local, meaning that they're dependent on a particular point in space. And that's not always true. There's some models which actually kind of integrate two-point correlations, and they're more exotic. But I don't think they're like more predictive. And by more predictive, I mean they don't always compare well any better than other models with experiments. So people, I guess, looking at different books on turbulence modeling, I collect them, I guess. A lot of them present K epsilon models first. And if you look back in our introductory material, we actually tried to describe in steps how to derive epsilon. So we already previously described how to derive epsilon, but omega was actually derived with dimensional analysis in the Soviet Union under Andrei Kolmogorov, and we'll look at that in a little bit. So I'll just note that epsilon can be derived analytically, and omega is formed traditionally by dimensional analysis. And these all fall generally under the Boussinesq approximation, which if you look back in your last chapter was introduced in 5.8. And the turbulent kinetic energy, which we introduced in equation 5.11. So we've already derived these equations, and you can flip back in your notes to check them out. And I believe in section 1.4, or section 4.1 of our notes, there's multiple ways to define, say, a length scale. And if you have two equations, like K and epsilon or K omega, you can actually write length scale as a function of, say, K and epsilon, and using different powers, or K and omega. And so for model closure, sometimes you want to derive time scales or length scales because we might know how they vary in these particular flows. So Andrei Kolmogorov academician and professor. He's probably the leading Russian-born mathematician, maybe of all time, or at least top 10 Russian mathematicians in the history of Russian math, I think. Created this so-called k-omega model. And he was the first one, and I'll show you that paper briefly when we talk about the model formulation. And he introduced this variable omega, and it has, unfortunately, multiple definitions, but it does have the dimensions of 1 over time. Okay? And that's a little bit different than epsilon, but there's ways to kind of relate epsilon to omega. So for example, it's possible to take a k epsilon solution and convert it to what you would believe a k omega solution and vice versa by relating epsilon is some function of omega. And depending on your k epsilon or k omega formulations, these formulas might be a little bit different. For example, in two equation models for omega, Kolmogorov's model is for omega, and other ones might be k omega squared models. So you even have to kind of look at these papers and the models and the codes and understand which one you're using if you want to convert back and forth. For the two equation models for epsilon, probably one of the first attempts to create an epsilon model and find closure coefficients was by Chao, 1945. I believe this was a Chinese person. I don't know much about that paper, but that's not like the standard paper today, which we'll talk about. Now I mentioned like these might be Boussinesq models and try and implement eddy viscosities and momentum equation. Well, probably the most common form to find a length scale in eddy viscosity, like I mentioned here, is with this equation. Eddy viscosity goes as the turbulent kinetic energy divided by the dissipation, and the length scale goes as k to 3/2 over epsilon. So if you have a steady Rand solution, you don't know anything about the length scale whatsoever. But you can estimate it, at least some kind of length scale. It's not necessarily an integral scale or a microscale or a Kolmogorov scale. It just goes as k to 3/2 over epsilon, and of course that has the dimensions in meters if you're an SI. And so that's one thing. In fact, you could try and, if you wanted, derive one equation models with combinations of k epsilon or k omega models, and that's exactly what we saw done in the previous one equation talk, right on Reynolds transport or Reynolds number type model, like Baldwin-Barth. And there's other types of models, and if we have time, we might just talk about different ones, and there's advantages and disadvantages. But one example is Rada in 1951. He proposed the first turbulent length scale model, and but then might have slightly different forms of how he did eddy viscosity, k to the half L. So if you have a KL model, you obviously don't have epsilon, so instead of epsilon, you'd have L to recover your eddy viscosity. Simple things. And there's other little models here just worth mentioning. 1986 model, K and tau. I believe that was one of the first appearances. In 1990 model, there's another type equation for tau. And these have different relations with respect to eddy viscosity, length scale, and epsilon. So it's basically you're just recovering the right dimensions. If you have whatever two equation model you have, to fit it in with, say, closure coefficients or auxiliary relations or getting into your momentum equation, just use different analysis for that. Okay, so you have lots of choices for the second variable, and there's two most popular, omega and epsilon. And just to summarize these, you might have dissipation, eddy viscosity, length scale, and these all have dimensions, and the equations can sometimes be found through dimensional analysis. And that's the historical way. So correlations and properties found through analysis. Whoops. And I should mention today, because it's contemporary, that people are using large LES and DNS databases to find correlations in closure, or they might try and involve some machine learning type algorithm to also find closure of some of these models for particular flows. I've mentioned this Stanford conference before between the Air Force, where they assessed a large number of models. Most of the models that people brought to be assessed were two-equation models. And a lot of the uncertainty in modeling is in the second order, or the second equation. So if it's epsilon or omega, how do we close the models? And one reason maybe omega is more popular historically is the omega equation seems simpler. And you'll see that when we present these equations. And it had some of the first well-closed coefficients for boundary layer flows and dissipation of like homogeneous isotropic turbulence. So just some additional notes. It's really unclear even today which model is superior. And it might even be an argument of which type of turbulence model is best overall. Is it a one-equation model, two-equation model, Reynolds stress, or something else maybe more exotic? So people are still kind of arguing about this today. I'm not sure these issues will ever be resolved. There's also some huge questions in the community. For example, we might say there's no mathematical basis or sound physical reason. There's no fundamental reason. That the Eddy viscosity should depend on these turbulence parameters or statistics, like K or omega, etc. And we would expect these models to be valid for equilibrium flows, but they're not really models which are formed and calibrated for flows, turbulent flows, which aren't in non-equilibrium. But nonetheless, we use these models and closures for those flows anyway. And I think the research into the turbulence modeling and their closures is due to it's an active research area. I was distracted by that. Anyway, I'll let you finish copying this. So let's look at K omega models first. And there's two reasons. One is because they were kind of created first or proposed first. And the second reason is that they're a little bit simpler to understand. And so the first one, as I mentioned, was created by Andrei Kolmogorov, and I think it was proposed in a 1943 paper. And that was in Moscow in the Soviet Union, right during World War II. So that's an interesting time to publish mathematical research. So I happened to pull that paper, the original one, not some translation. And here it is. It's in 3 pages. So let's just look at that briefly. And I have also posted an interpretation of this paper done out of the United Kingdom in the class website. So this is the journal Doc Lady, and here's Andrei Kolmogorov's name, and it's obviously in Russian, so we're not going to spend much time on that right now. And here's the three equations. So you see, really, it's a 3-page paper, well, 2.5 page, so first, second, and third. And ironically, or just coincidentally, right after this paper is a follow-on paper by A.M. Abakov, which was Kolmogorov's student. And if you're in the turbulence world, you probably see his name too a lot. So it's kind of interesting coincidence. But here's the equation. And you might say, well, there's actually 3 equations. Well, not really. This is an incompressible form. So this one's for the velocity. This one is for omega, which is we call specific dissipation. And B is a kind of a strange form of a turbulent kinetic RMS energy. I guess it's like turbulent kinetic energy, but it's kind of RMS energy. So this is like a kind of like a K equation in a different form. And we're going to repeat these equations and kind of look at them and their motivation for finding them. So there they are. You don't have to write this down. It's on the class website. And it's also repeated in the notes. So he didn't do this and find these equations through like a derivation. He had already like a Rand's average equation, and he obviously knew about the K equation, and to form a 2-equation model, he proposed a transport equation for omega. And he was inspired by some of the researchers in the United Kingdom. Now, he's done it on dimensional analysis, and he noted that the properties of the motion, which are most characteristic of turbulence, pertain to regions which have dimensions which are in small compared to L. So let's just talk about some of the philosophy of Andrei Kolmogorov before writing down his equation. So he viewed that turbulence is regions which have characteristics smaller than L, and L is some integral length scale, and L might be viewed as a mixing length. So that's just some length, large scale, length scale in the turbulent flows, which he looked at as the mixing length. And the turbulence is like a cascade, and about, let's see, 1943, so 2 years earlier, he published his most famous work called K41, which is how we talked about earlier, where you find what the small scale turbulence is, which would be called the Kolmogorov scale. And there's this whole range of scales between L and eta, and he called eta the inner scale. He didn't call it after himself, to be a little bit presumptuous maybe. And these strange pulsations in the flow drive energy to smaller scales, drive the energy to smaller scales, and that becomes what he's called as the cascade, which is well talked about today. And one view that he held strongly, which I think he corrected maybe 15 to 20 years later in his life, due to experiments and other researchers in the theory part of the world, was that this dissipation or frequency of the small scales, if you will, happens and depends only on small scales, eta. So that's a assumption which we find to be incorrect today. And he called this the dissipation, omega is the dissipation of energy in unit time and space, x and t. Now, he was thinking about closure coefficients, and you saw from his paper that he had proposed the basic 3 equations, a K-type equation, energy equation, a dissipation equation, specific dissipation in time and space, and of course a momentum equation. But you did not see any closure coefficients, and you didn't see any auxiliary relations like we have today. And there's probably a few reasons. Well, one is he didn't have all the knowledge that you could find from digital computers later, because they didn't have any digital computers that I'm aware of in Moscow at the time, especially for predicting flows. So he had no way of sort of like implementing and testing the model. And he certainly made attempts to solve the equations, but he wasn't able to. And so I think what he tried to do is just make dimensional analysis based on simplified fields, like the homogeneous isotropic turbulent field, which he was aware of. So it's good to make a few notes about this field, because that's one of the fields used to find closure coefficients in what is probably the most famous used K omega model, just K omega, which is the Wilcox model. And so let's make a few notes about this. And what does this mean, of course? I actually had a whole 2 or 3 classes on this, but I don't think we have time this semester. But we have a field, which means the statistics don't change in space, and a field, which means the statistics of turbulence don't change with rotation. So in these cases, once again, the same rules apply. There's L, and then there's scales. Maybe I should say this way, greater than scales of turbulence. And there's some small scale eta. It's homogeneous. And there might be, if you take, say, U or V or W or P or T, all your variables, you can take moments. In this case, you take moments of, say, velocities of various orders. Then the mean values of those components and their vector differences can be defined as 2 points in space-time. And if your flow's homogeneous and isotropic, then say the moments of velocity, or they call them structure functions, are only functions of, say, r, which is the distance between 2 points. So all these structure functions are only a function of distance between any 2 points. And you can move those points anywhere in space in a homogeneous isotropic field, and it'll always have the same statistics. So that's one reason they do this. And these moments, there's really 2 that are unique. One, Kolmogorov writes as BNN, and the other one is BTT, as sort of transverse and normal moments to a vector between points 1 and 2 in any points in the field. It's a 1 and 2. And it turns out that if R is small, maybe smaller than the Taylor microscale lambda, then these are proportional to, say, BNN and BTT. All these moments and higher order moments go as R to some constant A. And between the range of R greater than lambda and R less than L, they should be proportional to R to the 2/3. I can never remember these coefficients. And A might be some constant, which we don't know exactly. And this is actually published in, let's see, 1941 by the same author, Kolmogorov. So he had a powerful tool, and we're going to use these moments for closure when we try and actually close the K omega model in the Wilcox approach, because he used 2 flows to close his model, which we know something analytical about. In turbulence theory and statistics, there's really 2 major flows: homogeneous isotropic turbulence and the log law boundular flow. So by just using those two flows, you can actually close a k omega model. Kolmogorov tried to just close the model based on the homogeneous field, I believe. Other things people noted was that in a flow which decays continuously, which is homogeneous and isotropic, so say we have a wind tunnel and we have a honeycomb structure, we send the flow through it and we generate grid turbulence, and that kind of convects and decays over time. So if our probe is convecting with the flow, we should say the flow decaying proportional to two things. Well, first, the velocity decay will be inversely proportional to 1 over time to the 5/7. And the second major thing is we see that L grows as the flow convects as time to the 2/7. Excuse me, it's proportional to time to the 2/7 seconds. So the integral scale goes as time to the 2/7, velocity decays as 1 over time to the 5/9. So this was all published by a group in the Soviet Union that still exists today in Russia called TSAGI. And I visited TSAGI. It's on the east side of Moscow. And that's like the equivalent of NASA research. So in NASA, there's like the research directorate with all the research aerospace engineers. Traditionally, I think they reformed it today. But that out in TSAGI is like their Central Aerodynamics Institute. So who's heard of Joukowsky, like Joukowsky airfoil? So he was associated with this institute. So if you ever go there today, I'm not sure it's a good place to visit today. Unpopular to be American in the Ukrainian war. You can go out there and at least see the area. And they actually have some cool monuments outside like the fences of some of the famous people work there. But anyway, there's a paper out of there, and it came out in 1939. These were kind of estimated with theory, but they were actually validated with grid turbulence experiments done at TSAGI. So that's where the first work was done, and it's been collaborated and found to be the same elsewhere. Okay. So based on these two flows, which were kind of known to Kolmogorov, he wanted to propose this system of equations, and this is the system from his paper, the exact equation. So once again, this is a velocity equation. This is your omega equation, which is specific dissipation in space and time, per unit space and time. And this V is basically your energy type equation. So he had, instead of, like we typically write K, but K is not B here. D dt, once again, is material or total derivative. And I defined a few what the things are here. These equations, you have external forces, which we usually discount in high-speed aerospace type flows. You have V bar, that's up here, right, for your velocity equation. Okay, P is pressure. Oh, okay, here's a little difference. B is 1/3 of the sum of Vj prime squared. So that's basically looking at taking your components, summing them, squaring them, taking the average, and divided by 3. So if you write that out, that's 1/3 of the root mean square fluctuation velocity. Here in Kolmogorov's work, he called omega sometimes maybe interpreted as like a frequency, and he wrote omega should go as some c, a constant, times b to the half, which is 1/3 of the root mean square fluctuating velocity divided by a length scale. But of course, you wouldn't do that in the actual code if you program this, because you would just solve both differential equations. And there's a little bit different interpretation in his context of epsilon, right? So this epsilon here is not dissipation, right? Okay. So that's just his nomenclature. So let's just take a look at these. So what do we have in here? We have a few things. And instead of writing notes down here, you can make your notes here, but I'm going to look at the equations. We'll note that there's some constants, right? So we need unknown constants. There's A. Maybe we'll highlight them. There's A prime, A double prime. Those are some I see. And they're must be determined somehow. And practically, you would determine by calibrating with, say, measurement, right? So you would program this with your finite difference solver, perhaps, nonlinear solver, drive towards steady solutions, and you'd have to somehow optimize A prime and A double prime, which can be difficult. The first term here on 6.6, this right there, that's going to represent 2/3 of the rate of dissipation of TKE per unit mass of the fluid. So that'll be about 2/3 omega over rho. And the second term, this one, will represent 2/3 the energy which is given by the mean motion to the turbulent fluctuations. And I think Kolmogorov and others, even numerically, so that these equations are very hard to solve. I think anybody would say that. And even numerically. Also, the basis omega might have some criticism because there's no production term. And why would we have a production term in dissipation? And up here I mentioned that Andrei Kolmogorov, he didn't believe that like dissipation occurred or larger scales of turbulence could dissipate turbulent kinetic energy. It only happened to the small scales. So the biggest criticism here is pointed out later, and he realized later there's no production. And so just a few things to think about is, one, these equations aren't in a form which are easy or wonderful to program, which I'm not a CFD developer, so I don't completely understand all this myself, I'll be completely honest. And also, there may be missing some important physics. So other researchers following on wanted to correct some of these problems before they were useful, and also be able to find a kind of analytical way as possible to find the closure coefficients. Okay. And I should note, I guess, that in that paper, without presenting any results, academician Kolmogorov noted that these equations, they try to integrate numerically for a simplified pipe flow. And when I say integrate it numerically, it means he had a team of computers trying it out, which is pretty amazing because you have a team of people doing this numerical calculation when almost everybody in the Soviet Union at the time was either sent to the front to fight the German invasion or sent to factories to work. I find that quite remarkable that he had such resources. Here's a little quote I pulled out, and this one's from like a report of looking at these. It said, Landau remarked that Andrei Kolmogorov was the first to provide correct understanding of the local structure of a turbulent flow as the equations of turbulent motion should be constantly borne in mind, in his opinion, that in the turbulent field the presence of rotation of velocity is confined to a limited region, and its qualitatively correct equations should lead to such a distribution of eddies. It's an interesting quote by a famous person. And so a lot of people had this model, and there were multiple attempts to try and create one that's useful for CFD in our field. As I notice, K42 or 43, excuse me, I think it's 43, did this first two equation model, and he chose K in a slightly different form, and he introduced specific dissipation. And there was multiple attempts to kind of form better K omega models. And let's just look at some of those. Well, first, one was by Safman. And in this approach, he tried to improve some of the terms. And I'll just make notes of different models. I don't want to go through like a conference literature, but there's obviously Wilcox, who wrote multiple books, self-published. Safman, and Tracy. And there's a few, like over about 2 decades of research where they formed K omega models. A fellow named Coakley in '83 formed a K to the half omega model. People like Mentor, who we'll talk about later, and others also made K omega models, but they did blending, which is a Mentor shows transport model, which we'll talk about. And then others, even more, Robinson, a guy named Robinson in '95 made K omega squared models. So you can see there's even different forms. And I would say the most popular form today is these K omega models, and then coming second are K omega squared models. So Kolmogorov, like I mentioned, called this the rate of dissipation of energy in unit volume and unit time. And you can interpret that in a few different ways. Some might see it as a mean frequency, and it might go as omega c to the k half over L, where c is a constant. The reciprocal of omega is a time scale, right? So that would have the units of seconds, because omega is 1 over a second. And if you believe that omega can be defined in some way as a function of the eddies and their energy, then you could associate omega with dissipative properties. Turbulence. And you could also expect omega, another way to look at it, is to be proportional to k 1/2 over L, which I noted up there. And so that's the product of velocity and length scales, right? So that's proportional. I suppose that you can take other scales of turbulence and try and make simple dimensional relations. And you'll notice in that paper in Kolmogorov, he really didn't go into much of the derivation, just kind of explaining it in words as a philosophical, empirical type model, but it was based on dimensional analysis. And so that's one criticism that people might have of omega type models, is they're sort of based on this dimensional analysis and sort of philosophy of cascades and trying to form a model, but he was missing a term like production. So a lot of people wonder today, how did he come up with the model? And that's a topic of much discussion, yeah, even today. So let's kind of just talk about maybe his line of thinking. So it might be seen that K already appears in one equation, so it's very useful. And it's possible that, say, nu t is proportional to k or something like it, or goes as nu t. And the dimensions of nu t go as length squared over, say, time, while the dimensions of k go as length squared per time squared. I just use L and T, length and time. So what would the dimensions of eddy viscosity be? Eddy viscosity, with k, excuse me. So eddy viscosity by k, let's look at our dimensions. That should go as, say, length squares cancel, and that's 1 over time and time squared. So I think that goes as time. Okay, now what about turbulence dissipation? Turbulence dissipation is another dimensional variable, should go as length squared divided by time cubed. Well, if we look at dissipation divided by k, that would have the dimensions of 1 over time. So if we look at equations, I'll let you copy that for a second. So here's the clue. If we look at equations 5.8 to 5.11, where am I here? Whoops. Well, we can look at these two. We might try and introduce a variable with dimensions time or inverse time. Which would be omega. So the next step, once he's kind of written down these relations, was to postulate an equation for omega. And to do that, he only saw that there's certain processes happening in the turbulent cascade. And these might be some unsteadiness, some convection of omega, some diffusion, some dissipation, dispersion, and production. Well, he didn't really put that one in, and that's why I noticed that term is missing up there. So based on, I mean, nobody really knows, but this is sort of postulated based on a couple papers and also briefly mentioned in Wilcox's CFD modeling book, that Kolmogorov directly wrote down this equation based on these properties and this dimensional unit right here in equation 6.7. Let me finish copying that. And in his work, you can kind of look at this equation, compare it to the one I note here for omega, and it's written in a little bit different way, a more modern way. And so 6.7, you see a few different terms. Well, now we have a transport equation for omega, and there's no production term, but there is a coefficient b and a coefficient sigma here with nu t. So this is written so that there's two new closure coefficients. And typically I see in the literature, people put a equivalent little asterisk by, say, beta for a term like in k or sigma. So let's kind of finish up Kolmogorov's view, which will take a little bit more, so bear with me. So there's some interesting features of this equation. First of all, there's no production term, which is corrected later by other authors. And that's consistent with Kolmogorov's view that omega is only associated with the small scale structures, Kolmogorov scale, maybe to Taylor microscale region. And, you know, that was wrong. It's flawed because really these energy-bearing eddies L are primarily responsible for determining the appropriate time scale of the turbulence and the rate of dissipation itself. So large-scale structures are responsible also for dynamics of omega. And there's no molecular diffusion type term. Which is probably another issue. And so his model is only for high Reynolds number flows. And that probably makes sense because a lot of his theories, like his K41 theory, was for high Reynolds number anyway. So he would let Reynolds number become very far and very high. And the model really, when you think about it, because it's just laid down based on dimensional analysis and what he thought to be the important properties of turbulence, could be viewed as physical, but empirical. So that's nothing wrong with that, because it works really well. And I guess that's why some people viewed him as a genius. One might say, how do we interpolate omega, the specific dissipation? And there's a few different ways people even looked at it. So Safman, in 1970, he saw that it's a frequency characteristic of the turbulence decay process. Under self interaction. Other people like Spalding, who also is a turbulence modeler in Rand, wrote it's omega squared goes as twice the entropy. And maybe another one is omega, like Wilcox himself would just say omega goes as the ratio of epsilon to k, which is dimensionally correct too. So since the introduction of Kolmogorov's model in 1943, let's see, what is it, about 2022 today? That's about just over 70 years of research on the model, since it really came out of Russia. So over 70 years and counting of research, which is a lot. And most people, excuse me, form K omega models, like I mentioned, and some will be for omega squared. So to summarize the Kolmogorov's model, it's dimensionally correct. It's formed by dimensional analysis, intuition, by what might be viewed as a mathematical genius. And people took that model and tried to write it in forms which are amenable to computers with production and low Reynolds number, and went further and created closure coefficients. And the people who really did that maybe best is D.C. Wilcox in his K omega model in 1988. So I think we can take a small break here, maybe a few minutes. So come back at 12:45. How's that? And then we'll look at D.C. Wilcox model, okay?